Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 109, Teaching Neural Nets to Generalize the Way Humans Would, published on the 22nd of July 2020 by Rohin Shah. Highlights. Link Better Priors as a Safety Problem and Learning the Prior, both by Paul Cristiano, summarized by Rohin. Any machine learning algorithm, including neural nets, has some inductive bias, which can be thought of as its prior over what the data it will receive will look like. In the case of neural nets, and any other ML algorithm to date, this prior is significantly worse than human priors, since it does not encode, for example, causal reasoning or logic. Even if we avoid priors that depended on us previously seeing data, we would still want to update on facts like, I think therefore I am. With a better prior, our ML models would be able to learn more sample efficiently. While this is so far a capabilities problem, there are two main ways in which it affects alignment. First, as argued in Inaccessible Information, discussed in Newsletter 104, the regular neural net prior will learn models which can predict accessible information. However, our goals depend on inaccessible information, and so we would have to do some extra work in order to extract the inaccessible information from the learned models in order to build agents that do what we want. This leads to a competitiveness hit relative to agents whose goals depend only on accessible information, and so during training we might expect to consistently get agents whose goals depend on accessible information instead of the goals we actually want. Second, since the regular neural net prior is so weak, there's an incentive to learn a better prior and then have that better prior perform the task. This is effectively an incentive for the neural net to learn a Mesa optimizer, as discussed in Newsletter 58, which need not be aligned with us, and so would generalize differently than we would, potentially catastrophically. Let's formalize this a bit more. We have some evidence about the world, given by a dataset D, which is a set of pairs x1, y1, x2, y2, and so on. We assume that it's a prediction task. Note that most self-supervised tasks can be written in this form. We'll later need to make predictions on the dataset D star, which is a set of x1 star, x2 star, and so on, which may be from a different distribution than D. For example, D might be about the past, while D star is about the future. We would like to use D to learn some object Z that serves as a prior, such that we can then use Z to make good predictions on D star. The standard approach, which we might call the neural net prior, is to train a model to predict Y from X using the dataset D, and then apply that model directly to D star, hoping that it transfers correctly. We can inject some human knowledge by fine-tuning the model using human predictions on D star, that is, by training the model on a set which is pairs of x1 star, h of x1 star, x2 star, h of x2 star, and so on. However, this does not allow H to update their prior based on the dataset D. We assume that H cannot simply read through all of D since D is massive. What we'd really like is some way to get the predictions H would make if they could update on dataset D. For H, we'll imagine that a prior Z is given by some text describing, for example, rules of logic, how to extrapolate trends, some background facts about the world, empirical estimates of key quantities, etc. I'm now going to talk about priors over the prior Z. So to avoid confusion, I'll call an individual Z a background model. The key idea here is to structure the reasoning in a particular way. H has a prior over background models Z, and then, given Z, H's predictions for any given xi are independent of all the other xy pairs. In other words, once you've fixed your background model of the world, your prediction of yi doesn't depend on the value of yj for some other xj. Or to explain it a third way, this is like having a set of hypotheses and then updating on each element of D one by one using Bayes' rule. In that case, the log posterior of a particular background model Z is given by log prior of Z plus sum I log probability of yi given xi and z, neglecting a normalization constant. The nice thing about this is the individual terms prior of Z and probability of yi given xi and z are all things that humans can do, since they don't require the human to look at the entire dataset D. In particular, we can learn prior of z by presenting humans with a background model and having them evaluate how likely it is that the background model is accurate. Similarly, the probability of yi given xi and z simply requires us to have humans predict yi under the assumption that the background facts in z were accurate. So we can learn models for both of these using neural nets. We can then find the best background model, z prime, by optimizing the equation above, representing what h would think was the most likely background model after updating on all of d. We can then learn a model for probability of y star I given x star I and z star by training on human predictions of y star I given access to z star. This of course only gets us to human performance, which requires relatively small z. If we want to have large background models allowing for superhuman performance, we can use iterated amplification and debate to learn prior of z and p of y given x and z. There is some subtlety about how to represent z that I won't go into here. Rohin's opinion. It seems to me like solving this problem has two main benefits. First, the modeler AI system learns from data, i.e. the z star, is interpretable, and in particular we should be able to extract the previously inaccessible information that's relevant to our goals, which helps us build AI systems that actually pursue those goals. Second, AI systems built in this way are incentivized to generalize in the same way that humans do. In the scheme above, we learn from one distribution D, and then predict on a new distribution D star, but every model learned with a neural net is only used on the same distribution it was trained on. Of course, while the AI system is incentivized to generalize the way humans do, that does not mean that it will generalize as humans do. It's still possible that the AI system internally wants to gain power and only instrumentally answers questions the way humans would answer them. So inner alignment is still a potential issue. It seems possible to me that whatever techniques we use for dealing with inner alignment will also deal with the problems of unsafe priors as a side effect, in which case we may not end up needing to implement human-like priors. As the post notes, it may be much more difficult to use this approach than to do the standard neural net prior approach described above, so it would be nice to avoid it. Section Technical AI Alignment. Subsection Iterated Amplification. Link Alignment Proposals and Complexity Classes by Evan Hubinger, summarized by Rohin. The original debate paper discussed in Newsletter 5 showed that any problem in P-space can be solved by optimal play in a debate game judged by a problem-specific algorithm in P. Intuitively, this is an illustration of how the mechanism of debate can take a weak ability, the ability to solve arbitrary problems in P, and amplify it into a stronger ability, the ability to solve arbitrary problems in P-space. One would hope that similarly, debate would allow us to amplify a human's problem-solving ability into a much stronger problem-solving ability. This post applies this technique to several other alignment proposals. In particular, for each proposal, we assume that the human can be an arbitrary polynomial time algorithm, and the AI models are optimal with regard to their loss functions, and we ask which problems we can solve using these capabilities. The post finds that, as lower bounds, the various forms of amplification can access P-space, while market making, discussed in Newsletter 108, can access EXP. If there are untamperable pointers, so that the polynomial time algorithm can look at objects of an arbitrary size as long as it only looks at a polynomial-sized subset of them, then amplification and market making can access R, the set of decidable problems. Rohin's opinion. In practice, our models are not going to reach the optimal loss, and humans won't solve arbitrary polynomial time problems, so these theorems won't directly apply to reality. Nonetheless, this does seem like a worthwhile check to do. It feels similar to ensuring that a DeepRL algorithm has a proof of convergence under idealized assumptions, even if those assumptions won't actually hold in reality. I have much more faith in a DeepRL algorithm that started from one with a proof of convergence and then was modified based on empirical considerations. Link How Should AI Debate Be Judged? By Abram Dembski, summarized by Rohin. Debate, discussed in Newsletter 5, requires a human judge to decide which of two AI debaters should win the debate. How should the judge make this decision? The discussion on this page delves into this question in some depth. Subsection Handling Groups of Agents. Link What Counts as Defection? By Alex Turner, summarized by Rohin. We often talk about cooperating and defecting in general-sum games. This post proposes that we say that a player P has defected against a coalition C that includes P, currently playing a strategy S, when P deviates from the strategy S in a way that increases their own personal utility, but decreases the weighted average utility of the coalition. It shows that this definition has several nice intuitive properties. It implies that defection cannot exist in common payoff games, uniformly weighted constant sum games, or arbitrary games with a Nash equilibrium strategy. A Pareto improvement can also never be defection. It then goes on to show the opportunity for defection can exist in the prisoner's dilemma, stag hunt, and chicken. Whether it exists depends on the specific payoff matrices. Subsection Forecasting. Link Environments as a Bottleneck in AGI Development by Richard Ngo, summarized by Rohin. Models built using deep learning are a function of the learning algorithm, the architecture, and the task/environment/dataset. While a lot of effort is spent on analyzing learning algorithms and architectures, not much is spent on the environment. This post asks how important it is to design a good environment in order to build AGI. It considers two possibilities: the easy paths hypothesis, that many environments would incentivize AGI, and the hard paths hypothesis, that such environments are rare. Note that hard paths can be true even if an AGI would be optimal for most environments. If AGI would be optimal, but there's no path in the loss landscape to AGI that is steeper than other paths in the loss landscape, then we probably wouldn't find AGI in that environment. The main argument for hard paths is to look at the history of AI research, where we often trained agents on tasks that were hallmarks of intelligence, like chess, and then found that the resulting systems were narrowly good at the particular task but were not generally intelligent. You might think that it can't be too hard, since our environment led to the creation of general intelligence, us, but this is subject to anthropic bias. Only worlds with general intelligence would ask whether environments incentivize general intelligence, so they will always observe that their environment is an example that incentivizes general intelligence. It can serve as a proof of existence, but not as an indicator that this is particularly likely. Rohin's opinion. I think this is an important question for AI timelines, and the plausibility of hard paths is one of the central reasons that my timelines are longer than others who work on deep learning-based AGI. However, GPT-3, discussed in Newsletter 102, demonstrates quite a lot of generality, so recently I've started putting more weight on actually designing the environment won't be too hard, which has correspondingly shortened my timelines. Subsection Miscellaneous. Link Talk. Key Issues in Near-Term AI Safety Research by Aryeh Englander, summarized by Rohin. This talk points out synergies between long-term AI safety and the existing fields of assured autonomy, safety engineering, and testing, evaluation, verification, and validation, TEV&V, primarily by showing how they fit into and expand DeepMind's framework of specification, robustness, and assurance, discussed in Newsletter 26. Section Other Progress in AI. Subsection Reinforcement Learning. Link Using Selective Attention in Reinforcement Learning Agents by Yujin Tang et al., summarized by Sudhanshu. Recently winning a Best Paper award at Gecko 2020, this work marks a leap forward in the performance capabilities learned by small agents via evolutionary methods. Specifically, it shows that by jointly learning which small fraction of input to attend to, agents with only thousands of free parameters can be trained by an evolutionary strategy to achieve state-of-the-art performance in vision-based control tasks. The key pieces include self-attention over input patches, non-differentiable top K patch selection that affects inattentional blindness, and training via CMAES. By design, the agent is interpretable, as the top K patches that are selected can be examined. Empirically, the agent has 1,000 times fewer weights than a competing neural architecture, and the method shows robustness to changes in task-irrelevant inputs, as the agent learns to focus only on task-relevant patches. Sudhanshu's opinion. The parallelism afforded by evolutionary methods and genetic algorithms might be valuable in an environment where weak compute is plentiful, so it's exciting to see evidence of such methods besting GPU-hungry deep neural networks. However, I wonder how this would do on sparse reward tasks, where the fitness function is almost always uninformative. Finally, while it generalizes to settings where there are task-irrelevant distractions, its deliberate, sharp self-attention likely leaves it vulnerable to even simple adversarial attacks. Link Improving Sample Efficiency in Model-Free Reinforcement Learning from Images by Denis Yeratz et al., summarized by Flo. Sample efficiency in RL can be improved by using off-policy methods that can reuse the same sample multiple times, and by using self-supervised auxiliary losses that help with representation learning, especially when rewards are sparse. This work combines both approaches, by proposing to learn a latent space representation using an autoencoder, while jointly training an agent on that latent representation using SAC, discussed in newsletter 42. Previous work in the on-policy case shows a positive effect from propagating actor-critic gradients through the encoder to improve the usefulness of the encoding for policy learning. However, this destabilizes training in the off-policy case, as changing the encoding to facilitate the actor also changes the Q function estimate, which in turn changes the actor's goal and can introduce non-stationarity. This problem is circumvented by only propagating the Q network's gradients through the encoder while blocking the actor's gradients. The method strongly outperforms SAC trained on pixels. It also matches the previous state-of-the-art set by model-based approaches on image-based continuous control tasks, and outperforms them for noisy observations, as these make dynamics models hard to learn. The authors also find that the learnt encodings generalize between tasks to some extent, and that reconstructing the true environment state is easier using their latent representations than using a representation obtained by training SAC on pixels directly. Methods like this, that can benefit from seeing a lot of action-independent environment observations, might be quite important for applying RL to the real world, as this type of data is a lot cheaper to generate. For example, we can easily generate a ton of observations from a factory by equipping workers with cameras, but state action next state triples from a robot interacting with the factory are very costly to obtain. Subsection Metalearning. Link AutoML0, Evolving Code That Learns, by Esteban Real, Chen Liang et al., summarized by Rohin. While Neural Architecture Search, NAS, typically searches for, well, architectures, it would be nice if we could learn the full ML algorithm rather than just the architecture. This paper does exactly this. It defines a simple domain-specific language, DSL, for linear algebra and probability computations, and then uses a simple evolutionary algorithm to find programs in this DSL that get high accuracy on a classification task. The evolutionary search rediscovers many of the ideas in machine learning, including gradient descent, bilinear models, and gradient normalization, over the course of evaluating 10 to the 12 algorithms. Rohin's opinion. It's cool to see automation of even the ML algorithms themselves. However, note that there's no deep learning or function approximation in this system. It is a simple search algorithm that's commonly used in program synthesis. In fact, though the paper is presented as an ML paper, it seems to me much more like a classic program synthesis paper that happens to be working in the domain of ML algorithms. Without any learned heuristics, these algorithms have a hard time scaling. They can only synthesize relatively short snippets of code, since the search space grows exponentially as the code gets longer. Good results depend very strongly on being able to create a DSL in which the correct program is short. In this case, it looks like strong programs are about 20 straight-line instructions, which seems on the more impressive side given the simplicity of the algorithm and the DSL, though they did throw a huge amount of compute at the problem. This concludes Alignment Newsletter number 109. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.